Okay, so we've got a question from our live audience here at Physics on Friday, to be the name of our webcast. And so, Andre, you had a question. Go ahead.
Yeah.
Hold on a second.
So I was just wondering, with these instantaneous rates of change, if they exist in the world that we live in, like if there is, could you give us an example?
Okay, that's a great question. So if you're driving your car cannot change its velocity or its acceleration instantaneously. However, at the scale of atoms, everything happens in discrete or quantum steps. So, for example, if an atom gets hit with a photon, its energy doesn't slowly go up to a new level, it changes instantaneously. So at the quantum level, things change instantly, but at the macroscopic level, the level that we experience from a day-to-day basis, things change in a non-instantaneous or continuous way. Those would be the two words. So there are things that are instantaneous. I hope I spelled that right. And there are things that are continuous. Continuous. Now, the other way to say this, instantaneous, or the other word for it, which is used, is discrete. I can't spell up close. I've talked about this disability before. When I'm writing up close to a board, I can't spell. It's true. It really is true. Huh? C-R-E-E-T? No, there's two types of discrete. Yeah. Okay, so this is an instant. Okay, anyway, good. Now, let's talk about these graphs again, but this time we're going to go the other way. Okay? We are going to start with a graph of, let's draw an arrow here. Okay, there's my axes. 1, 2, 3. This time we're going to start with acceleration. And then we're going to go to velocity. And then we're going to go to position. Yep, position. Okay, so this time I'm going to draw a graph that doesn't have any instantaneous changes of acceleration. Okay, so I'll just draw a graph that's curved. So let's say my acceleration, I'm accelerating at a constant rate, and then I slow down, and my acceleration is now here, and then my acceleration stops. Now remember, you got to wrap your mind around this. Acceleration is how fast you're gaining speed in a given amount of time. Okay? So if we do velocity now, I'm gaining velocity at a constant rate all the way up to the knee in the curve. This is the knee of the curve right there. So I'm going to draw my division line here like that. Okay. So now let's do my velocity graph. So what do you think it's going to look like, Andre?
It's a positive acceleration, so velocity is going up.
Yeah. So picture this. Okay, you're in your car, you're driving, you got your pedal to the metal. So you look at your speedometer. What's your speedometer doing over time? It's going up. So here's my speedometer. It's going up and 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 up. And then you take your pedal off the metal. So you let up on the accelerator. And now your velocity is still increasing. It's just not increasing as fast. So now your velocity is still going up, but just not quite as fast. And then you let go of the gas altogether and you put your cruise control on. So now you're going at a constant velocity. So your acceleration isn't changing anymore. And so now that's a straight line. So that's the velocity curve you get from this acceleration curve. Okay? It's a little counterintuitive. You got it. That's the continuation of that acceleration curve. Michael?
Now, the acceleration doesn't affect the velocity at all, right?
No, if you're accelerating, your velocity is going up.
Right. But after you stop accelerating on the acceleration part of the graph, it looks like the acceleration is going down to me, but that shouldn't affect the velocity at all.
Right, because now you've got zero acceleration, so your velocity stays constant.
Your velocity won't drop.
Your velocity is only going to drop if the acceleration goes negative. Andre, did you have a comment or a question?
No.
No? Okay. So then we're going to go from velocity to position, and basically your velocity is increasing, so your speed, which is the magnitude of the velocity. We talked about vectors. Velocity is a vector quantity in the last class, so the magnitude of the velocity is the speed. Your speed is increasing for this whole first portion of this graph, so your position is going to increase. So position's increasing, then your position is increasing some more, but not quite as fast. But hold on, I gotta change this a little bit. Then your position is increasing some more, but not quite as fast. But then even after you stop accelerating, you still have velocity, so your position still continues to, hold on a second, made a shape I didn't mean to make. Your position still continues to increase, but again, just more slowly now. And I'm trying to make the slope of this be different than the slope of this. I just didn't draw it quite right. Okay?
So the position determines basically just how far you're going.
How far you've gone.
Okay.
How far you've gone at a given time t. Now, watch this. This is getting into a neat thing, which I'm not going to name yet. Some of you might know what this is. If I take the area under the curve or under my graph for acceleration, that area is going to tell me hold on a second. So if you take the area under that curve, so just for example, say this acceleration here is 1 meter per second, and this is after 10 seconds. Area equals length times width. So in this case, area is going to equal 10 seconds times 1 meter per second. And so the area is going to equal 10 meters per second, right? Hold on a second. Don't worry. If you're a little lost, don't worry. I made a slight mistake here. I'm going to erase it. Here's the point. Let's just leave the units off right now because that's the part that's going to confuse us. If we just say the length is 10 seconds and the acceleration is 1 meter per second, and really should be meter per second squared, but we'll just leave that, equals 10. Okay? That means this point here is going to be 10 meters per second, right? So the area under the curve tells us our new velocity. Same thing here. If we do this area right here under this part, it will tell us what this point is. Likewise, if I take this area here under the velocity curve, it's going to give us our new speed, or our new position. Okay, so this is, instead of using, remember we used slope in the last part of the lecture. In this part, we're using area. And the big fancy name for this type of math is called what, Andre? Calculus, right. But so calculus is not really that bad. What it is a way of using these areas and things under curves to give you information. So the area under your graph of acceleration tells you something about the velocity. The area under the graph of the velocity tells you something about the position. So you can go between these three graphs by either using slope if you want to go one way, or using area and you can go the other way. So this all has to do with simply tracking the position of an object. And your book talks quite a lot about this in the first chapter, which is called Unit 1, but it starts with Chapter 2. So I'm sure you all saw that in your book. So now we'll continue, and we'll start getting into some of Newton's laws.